Hello everybody, in this video I will introduce to you let's consider this signal xt which has a non-zero amplitude from t equal to 0 to t equal to 3, and this signal is called a continuous time signal. From t equal to 0 to t equal to 3, there are actually an infinite number of points with values of 2. So that's why this signal is called a continuous time signal. When we apply sampling process to this signal, let's say we apply sampling at t equal to 0, t equal to 1, t equal to 2, t equal to 3, and so on, what we get is actually what we call discrete time signal or digital signal. So this signal has numbers of values at a certain point of time t. To differentiate between the continuous time signal and the discrete time signal, the x-axis uses n for the discrete time signal instead of t for the continuous time signal. This figure shows a system which has one input and one output. A system is an operator that maps input signal to an output signal. Now let me introduce the linear time invariant system. A linear system has three properties. The first one is called additivity property. The second property of a linear system is scaling property. And the third property is called superposition property. Now, let's say the system receives x1 as the input and y1 as the output. Let's say the same system receive a different input called x2 and produce, of course, a different output y2. Now if we add x1 and x2, okay, x1 plus x2 as a signal, and this signal is the input to the same system, and if the system produce the addition of y1 and y2, which is y1 plus y2, then we can call the additivity property is valid for the system. Now we have a system that produce y1t as the output from the input x1t. For the same system, if we apply amplitude scaling to the input and the same scaling is also applied to the outputs, then the scaling property is valid for the system. As you will see, the superposition property is actually the combination of the additivity property and the scaling property. What is time invariant system? A system is called a time variant if the behavior of the system is not depends on time t. In this simple example, if yesterday a system produced yt as the output from the xt as the input as of yesterday, and today the system also still behave the same, given input xt, the system produce the output yt, and the same goes to tomorrow and day after tomorrow and so on. So in this system, since the behavior is not depends on time, then we can say that the system is a time invariant system. The blue box in this figure represent a linear time invariant system which has an impulse response ht, an input signal xt, and an output signal yt. Why the ht is called impulse response? The impulse response is obtained when the input to the LTI system is an impulse signal delta t. For an LTI system which has impulse response ht, input to the LTI system is xt and the output is yt, then the relationship between the xt and the impulse response ht is given by the yt as a convolution between xt and ht. Mathematically, it is given by the integration of tau from minus infinity to infinity of the multiplication of x tau and ht minus tau. Similarly, this is also can be computed by using the second equation. So based on these two equations, before the integration is calculated, we have to multiply two signal, x tau with ht minus tau, or h tau with xt minus tau. Note that we use this symbol to represent the convolution operation. The convolution has three properties. The first property of convolution is commutative property. Commutative property indicates that xt convolution with ht is equal to ht convolution with xt. The second property of convolution is associative property. Basically, if the convolution involve three different signals, xt, h1t, and h2t. At the left side of the equation, the convolution of xt and h1t is applied first. After that, the output of the convolution is subjected to the second convolutions with h2t. At the right side of the equation, h1t and h2t are subjected to the first convolution. After that, the output of this convolution is subjected to the second convolution with xt. For the case of convolution of three different signals, we have to select two signals for the first convolutions, and then the output of the first convolution is subjected to the second convolution with the last signal. So in this case, it is up to us. For the first convolution, we want to apply convolution to xt with h1t, or we want to apply convolutions to the h1t and h2t first. The third property of convolution is distributive property. Basically, the first signals involved in the convolution is xt, while the second signal actually the addition of h1t and h2t. Basically, what we can do is that at first we apply convolution to the xt and h1t, and then we apply the second convolution to the xt with h2t, and then we add this to output of the convolution. Now consider the following example. We have one LTI system. We want to find the output of the LTI system YT. The input to the LTI system is xt, and the impulse response of the LTI system is ht. The xt and the ht are given as follows. This question requires us to calculate a convolution of xt and ht. So using this convolution integral, firstly we have to multiply h tau with xt minus tau and then do the integration of tau from minus infinity to infinity. The question is, given ht, how to find h tau? Basically, the shape of ht is similar to the h tau. The only difference is that the domain. We change the domain from t to tau. The next question is how to find xt minus tau from xt. This is xt. At first, we just change the domain of the signal from t to tau. In this stage, the shape of the signals is still the same. After that, we apply time inverse operation to x tau in order to get x minus tau. So now we apply a time shift operation to the x minus tau signal, the variable for the time shift operation in this case is t, and t is a variable, which means that the value of t will varies from minus infinity to infinity. This is important. X minus tau minus t is also equal to x t minus tau. So as the value of t varies, the location of the signal also varies. If the t value varies from minus infinity to infinity, then the signal will actually shift from minus infinity to infinity as well. The orange signal is h tau and the green signal is x t minus tau, and this animation shows that the x t minus tau shift along the x-axis from minus infinity to infinity as the t value increases. Note that we want to do integration of tau from minus infinity to infinity. So we have to do this segment by segment or case by case. The number of cases is actually depends on the shape of the two signals involved in convolution. So in this example, there will be 3 cases, and the case number 1 is when t minus 2 is less than 0 or t is less than 2. So first, based on this condition, we multiply h tau with x t minus tau. Based on the pointwise multiplication, the multiplication will produce a zero amplitude signal, and thus when we do the integration we will get 0 as well. As the signal shift to the right, the case number 2 happens when the value of t in between 2 and 4. Similarly, based on the convolution integral, for this particular situation, again we multiply h tau with x t minus tau, and the output of the multiplication is as follows. So as we can see, the output of the multiplication has non-zero amplitude from 0 to t minus 2, and these non-zero amplitudes have 1 over 2 values. When we solve the integration, the results of the integration is equal to t minus 2 over 2. As the signal further shift to the right, we will have the third case, which is valid when t is greater than 4. The multiplication of h tau with x t minus tau will produce the following graph. The integration of this graph is equal to 1. Now we can write the answer, which is the output of the convolution process called yt for every cases, or for t from minus infinity to infinity. To test your understanding, try to do the following example. That's all. I will see you in the next video.